Gentlemen, we've made it finally to episode 7, the last and final episode on one of the most complicated subjects for this unit, non-freefall. And it's complicated because we're finally dealing a little bit more with reality. A lot of times, physicists like to simplify things so that we can understand the underlying physics, the basic physics of motion. But when you add in the complications of real situations, things do get a little bit more difficult. Non-free fall is what you would experience and what you observe in everyday life. Because when an object falls through the air, it's going to experience not only the force of gravity that's pulling it downward, but also the air drag of the air. The air actually resists the motion of the object falling through it, and it points upwards. Air drag is actually, as I mentioned in an earlier episode, a form of friction. Take again the example of a couple of bricks falling through the air. Now in free fall, their acceleration is equal to g. Their acceleration is that constant, the constant acceleration of free fall. However, in non-free fall, you have to take into account the force of air resistance. And the force of air resistance opposes the motion of the objects in free fall. It opposes the force of gravity. Let's say you have these two bricks falling in the air, and they're falling at a certain speed. The air is going to resist the motion of the bricks, and that arrow there represents the force of air resistance. It's acting in the opposite direction as the force of gravity. Gravity is pointing downwards, and the force of air resistance is pointing upwards. When you take air resistance or air drag into account, then the acceleration of the objects is no longer going to be g. G is the acceleration of objects only in free fall. So when you have air resistance, the acceleration of the objects ends up being less than g. This is the acceleration for objects that are falling in the situation of non-free fall. In non-free fall, then, the acceleration of fall is less than g, and it occurs when the air resistance is non-negligible. Remember, negligible means that there's hardly any of it. If I say that the air resistance is negligible, I mean that there's hardly any air resistance. We can discount it, we can ignore it. But if I say it's non-negligible, that means we can't ignore the air resistance. And you have air resistance when you have a couple of different things. You have the speed and the frontal surface area. If you have a parachute, it has a lot more surface area than, say, a rock. The rock has a much smaller surface area, and it's common sense. There's less air resistance with the rock than there is with the parachute. The parachute has a greater frontal surface area. Secondly, air resistance depends on the speed. The faster the object is falling, the more the air resistance is. You can understand this if you've ever been on a motorcycle maybe or something like that. The faster you go, the more you feel the wind in your face. The faster you're moving, the greater the wind is resisting your motion. Another example for speed. Air resistance increases with speed. It increases with speed, as you might understand if you were driving along the highway. When you drive along the highway, you hear the wind a lot more than when you're just driving along city streets because there's a lot more air resistance on the highway. You're going at a much faster speed. So air resistance depends on both speed and frontal surface area. The more the frontal surface area, the more the air resistance, and the greater the speed, the more the air resistance. Now what happens when the object is moving fast enough that the force of gravity equals its air resistance? When you have, in other words, this situation. Let's say that the red arrow is the force of gravity, and the green arrow pointing upwards is the force of air resistance. When the two equal each other, then you have no net force. Then you have this situation. The force of gravity is a vector, and it equals the force of air resistance, which is also a vector. and they're in the opposite direction, which we'll represent with a little negative sign. If they're in the opposite direction, then the sum of the two forces, Fg plus Fr, equals 0. I've put this little negative sign to indicate that, in fact, the forces are in opposite directions. Remember, with vectors, you have to take into account the direction of motion. And so when you add the two together, you have no net force and therefore no acceleration, which means that the velocity does not change. When you have no acceleration, does the object continue to move? Yes. If you have a parachutist falling from an airplane, eventually the air resistance on the parachute is going to cancel out the weight of the skydiver. At that point, though, the skydiver doesn't just stop moving, he's achieved his terminal speed. Terminal speed occurs when acceleration terminates. This word means that the acceleration ends up being 0, when the air resistance equals the weight and the net force is 0. If net force is equal to 0, then the acceleration is equal to 0. We also talk about terminal velocity, same thing as terminal speed. We're just specifying now the direction. Remember, a vector is like or for speed rather, speed is high school and velocity is college, right? So velocity is speed that's graduated from college, gotten more information, namely direction. Just a way of thinking about it, an analogy to think about it. So here's an example, physics students. Let's say that you want to go skydiving. Okay? So you jump from your plane. Initially, weight is the only force acting on you until you get some air resistance. As you start to fall faster and faster, the air resistance on you builds up, reducing the net force overall, because remember, air resistance is a form of friction. Friction is acting in the opposite direction of your direction of motion. So as you're falling downward, the air resistance is acting upward, reducing the net force, making the total acceleration decrease. When the air resistance equals the skydiver's weight, the net force is 0 and your acceleration terminates. When the diver reaches terminal velocity and then is going to continue to fall at constant speed. So after you reach your terminal velocity, after you reach your terminal speed, your speed at that point is the speed with which you'll hit the ground. Your speed isn't going to increase anymore after you've reached terminal velocity. So when we experience non-free fall, your speed doesn't just increase and increase and increase. It increases up to a certain point and then it terminates. Then it just continues at that speed because you're no longer accelerating. The air resistance has canceled out the force of weight. Time for some questions now. You have a 20 Newton falling object. Remember, 20 newtons, that's the weight of the falling object. It encounters 5 newtons of air resistance. The acceleration of the fall is what? Less than g, more than g, or terminated? Pause the video now as you choose your answer. The correct answer is that it is less than g. Acceleration of non-free fall is always going to be less than g. In this case, it would actually be 7.5 meters per second squared, and the way you get that is from Newton's second law. Acceleration is equal to the force divided by the mass. Remember, this is the net force. So the net force is 20 newtons minus 5 newtons. 20 newtons down and 5 newtons up. So 20 newtons minus 5 newtons. And then the mass of the object is 2 kilograms. So you divide by 2 kilograms and you get 7.5 meters per second squared. Now, how do you know that the mass of the object is 2 kilograms? Well, we know that this is the weight of the object. It weighs 20 newtons. And weight is equal to mg, right? Weight is equal to the mass of the object times the acceleration of the object in free fall. That's simply the definition of weight, which we had from an earlier episode. And so, if the weight is 20 newtons, and we know that g is 10 meters per second squared. You divide both sides by 10, and you get m equals 2 kilograms. If you're still confused as to how I calculated the mass of the falling object, ask me in class and I'll explain it in further detail. Your next question. If a 50 Newton person is to fall at terminal speed, then the air resistance needed is less than 50 newtons, or 50 newtons, more than 50 newtons, or none of the above. Pause the video as you determine your answer. And the correct answer was 50 newtons. If 50 newtons is the air resistance, it cancels out the 50 Newton weight of the person. The sum of the forces equals 0, and acceleration equals 0. Remember, the symbol there that you see next to sum, let me underline it for you. This symbol means the net force, the sum of the forces. So I'm adding the 50 newtons, and I'm subtracting the 50 newtons of air resistance from the person's weight. That gives you 0, and then the net force is 0, so the acceleration is 0 as well. Now try this series of questions. As the skydiver falls faster and faster through the air resistance what? Increases, decreases, or remains the same, or not enough information? Pause the video to determine your answer. And the correct answer is air resistance increases. Remember, air resistance increases with speed. So as the skydiver falls faster and faster through the air resistance increases. Next question. As the skydiver continues to fall faster and faster through the air, net force increases, decreases, remains the same, or not enough information. Make sure you pause the video. The correct answer was that net force decreases. Why? As the skydiver is falling, the air resistance is increasing. Air resistance is a force, and it's pointing in the opposite direction as the skydiver's weight. It's increasing and canceling out more and more of the skydiver's weight. And as it cancels out more and more of the skydiver's weight, the total sum of the forces acting on the skydiver is decreasing. Last question now. As the skydiver continues to fall faster and faster through the air, her acceleration increases, decreases, remains the same, or not enough information. Think carefully now about this problem, and remember Newton's second law. Net force is directly proportional to acceleration. So if you change the net force, then the acceleration is going to change in the same way as the net force changed. Pause the video as you carefully select your answer. And the correct answer was her acceleration decreases. Take a look. Net force decreases. Her acceleration decreases. Acceleration changes in the same manner as net force. The skydiver's acceleration is decreasing, which means that with each passing second, the skydiver is gaining less and less speed. The questions have been sequenced so that you answer this last question correctly. Go back over the series of questions and ask yourself, would you have gotten it wrong if it had been asked first? We're going to finish out freefall in a second and final video, so as not to make this one too long.